Okay, so thanks a lot for the introduction, and also thank you very much to all the organizers for no, posso parlare in questo for organizing this very nice and interesting workshop, and also for inviting me. Okay, so today I would like to talk about this about a certain connection between black hole perturbation theory on one side and Cyber-Witten theory on the other. But I will try to put that in a slightly more general context, which is the one of topological string theory. Okay, and yeah, so we will see how it goes. And yeah, so what I'm going to talk about is based on several work which I did together with many great collaborators, some of who are also here in the audience. Okay, so as I said, let me start a little bit from a generic point of view. Okay. So when we think of string theory, for example, one of the main motivation behind this theory is the fact that string theory provides us with a very powerful framework to address this very hard question of unifying general relativity and quantum mechanics. Okay. However, this is like a very hard question, okay? But what we noticed during the last more or less 30 years is that in trying to concretely address this very hard question, string theory have developed many beautiful new ideas and also several tools which have given us many interesting applications in various different fields. Now, this type of application very often are a consequence of what we call string dualities. Okay, so roughly speaking, string dualities are relation between different type of object or different type of theory. And when we look at this object from a generic point of view, they look like very different. But then when we think of them from the point of view of string theory, we can typically see some hidden connection. And it's thanks to this hidden connection that then we have all these interesting consequences. And one of the first and also a very beautiful example of string duality is mirror symmetry. Okay, so in this case we have a relation between two different geometries, and the underlying intuition leading to this type of connection comes precisely from the fact that when we consider string propagation on those spaces, then this propagation is actually identical. Okay, and this is what led to this type of connection. And having this new relation mathematically is beautiful on its own, in some sense, but it's actually also useful for practical application because it allows us to map hard problem on one side to much simpler problem on the others. Okay, and this type of practical application where we can map something hard to something easier is something that show up very often in this string duality context, and is one of the reasons why they are so useful. A second important aspect on which we will also come back later in this talk is the fact that in this framework, sometimes we can relate a geometrical object to something which is more algebraic. Okay? And one of the first examples in this context is the work of Witten and Kontsevich, where we can relate intersection theory on the moduli space of Riemann surfaces on the geometric side to matrix model on the other. Okay, so if we push this point of view even further, then we can also think of geometry itself as some kind of emergent phenomena from more algebraic degree of freedom, right? And since typically we have a relatively good control over this algebraic degree of freedom, we can use that as a guideline to study, for example, what are the quantum modifications to the classical geometrical structure. Okay, so this is a second point on which I will come back later. And a third point, which I will also discuss more in detail later in the talk, is the fact that thanks to this duality, we can have a non-perturbative definition of string theory, right? And if we want to, fully understand a physical theory, we need to be able to go beyond perturbation theory. Okay? And duality allow us to precisely do this type of, to deal with this type of problem. And one example where this is very manifest is, for example, the case of the ADS-TFT correspondence. Okay. Okay, so that's the plan of the talk. So here I just tried to give some kind of generic introduction and motivation to introduce a little bit the main ideas. What I would like to do now is to illustrate some of these ideas concretely in a particular model, which is the one of topological string theory. Okay, and then we will see some application of this to the study of black hole perturbation theory. And in particular, I will focus on a subclass of quantity, which are black hole quasi-normal modes. Okay. And yeah, sorry, I have to drink. Okay, so let me start with topological string theory. And if you have any question at any time, please interrupt me. Okay. Okay, so as most of you probably know, like the main idea in string theory is that we replace point particle by strings, right? And formally, we can model this by considering map from a certain Riemann surface into a target space, which I will denote by X, okay? So let me elaborate a little bit more on this. First, Riemann surfaces, okay? So how do they arise in this context? So Riemann surfaces emerge when we consider periodic trajectory of closed strings, okay? Like here we have an example, right? This is a closed string, okay? So here the time goes in this way. And yeah, I'm not very stable with the pointer, but so we have our string which propagate, and here it's split in two, okay? These two propagates and then they join, okay? So this type of trajectory where we have one splitting and one joining generate a genus 2 Riemann surface, right? And in general, if we have multiple splitting and multiple joining, we have genus G Riemann surfaces. And then the detail of this process are encoded in the genus G free energy, which we typically denoted by FGs, okay? And the detail of the type of string model that we are considering are encoded precisely in this quantity here, the free energies. So here we have a genus 2 Riemann surface, so the detail of this process are encoded in F2. And then, as usually when we do this type of diagrammatic expansion, we weight each process by an appropriate power of the coupling constant, okay? In this case, we have the string coupling constant, which is denoted by GS. And since here we have two interactions, one splitting and one joining, we have 2 powers, okay? And then, but then this periodic trajectory, right, the trajectory of our string take place in a target manifold. So what we do typically is that we are interested in studying embedding of Riemann surfaces into a given target manifold. And for the purpose of this talk, we will consider a particular subset of target manifold, which are three-dimensional complex manifold. More precisely, we will consider a class of non-compact Calabi-Yau manifold. Okay, so this is the setup. And then what characterizes topological string theory is the fact that the free energy of this model encode in a precise way the enumerative geometry of the target manifold. Okay. So what does this mean? This basically means that we can write explicitly this genus G free energy in this way here. Okay. So our first point is that, as you can see here, you have an infinite sum, okay? But this infinite sum is actually convergent, okay? So this is a perfectly well-defined quantity. This number here, these are what are called Gromov-Witten invariant. And what they do, basically, they count holomorphic maps from a Riemann surface of genus G into our target space. Okay. So G here refers to the genus of the Riemann surface. G instead is the degree of the map. Okay. So these are maps which wrap two-cycle in the target manifold, and d is the number of wrapping. Okay. Then we have exponential of minus d times t. T is what is usually called the Kähler parameter of the target geometry, and it's like the area of the degree 1 map. Okay. And probably the most important point for what we will discuss today is the fact that for the type of geometry that we are interested in, this quantity have been computed explicitly. Okay, so we know precisely what these free energy are for the type of geometry that will enter in the discussion today. Okay, and then, so this is genus G free energy, so it refers to a particular type of process where we have a certain number of splitting and number of joining. But then what we typically do is that we define the full partition function by summing over all processes, right? And this is what we do here, which basically means summing over all genera, right? And in principle, that could be absolutely okay, but in this case, it's not. And one of the reasons, well, the reason is because here we have, again, a sum, an infinite sum. And the problem here is that this infinite sum diverges. Okay. So this is an asymptotic series with zero radius of convergence. And the way in which you see that is that you can compute this genus G free energy explicitly, and then you can see that when the genus is large, this coefficient grow factorially. Okay, so they grow too fast, and this gives rise to divergences. But this is actually something that happens very often in physics when we do perturbation theory, right? And typically, this is an indication that perturbation theory is not capturing the full physics of our system. Okay, so if we fully want to understand the model, we need to be able to go beyond perturbation theory. And this is the question of finding the non-perturbative completion. Okay. Do you have any questions so far? Okay. Okay, now, currently, I think it's fair to say that we do not have a complete understanding of this non-perturbative correction, and also what are, for example, the geometrical structure that describe them, right? So in the same way in which the perturbative expansion is encoded in this Gromov-Witten invariant, there should be something similar which is behind this non-perturbative effect. And so far, we do not really have a complete understanding of this point. However, as I was mentioning at the beginning, there is a successful framework where we can ask this type of question, and this is the framework of dualities. Okay. So, in our example, the question is, yes?
Is the expression borrow summable? Can you do some? Okay, you're going to talk about.
No,
okay.
It's a good question. I was not planning to touch this point. Okay. So it depends very much on which on the value of the parameter that you take. For example, you can take t. Let's take t real, and then you ask for Borel summation around the real line. It is Borel summable. Okay. But actually, Borel summation is one way to dealing with asymptotic series, but it's a, let's say, a numerical way of getting a number out of asymptotic series. But it doesn't really give you a lot of analytic information. Okay, so what I will be doing here is something that is not Borel resummation. It's something which is analytic, and actually the type of non-perturbative completion that I will be talking about does not agree with Borel resummation. Okay, yeah, but yeah, it happened. No, I can. You was referring to the quantum mechanics model with quartic potential, right?
Yeah. It means that you are probably in the wrong instantone sector. That's
exactly. Also, when you take this is the work of Balian, Parisian, Voros, right? If you take, for example, in quantum mechanics, you take the just pure quartic oscillator. also there, Borel summation does not give you the exact energy level that come that you can get, for example, by doing the numerical analysis of the operator. And what is happening here is actually very similar. And it's a very interesting question, but I will not discuss Borel summation. But thank you for the question. Okay, so instead of doing Borel summation that you can also do, what we will take is a more analytic approach. Okay. And in particular, what we found is that this enumerative geometry picture has a dual description in terms of operator theory. Okay. And in particular, this involves a certain class of quantum mechanical operators, which are called a quantum mirror curve. Okay, and I will come back on that in a moment. But for now, let me just be a little bit sloppy. Okay, so the type of operator which appear here are quantum mechanical operator on the real line. Okay, so they take this form here, where x and p are the position and momentum operator. Okay, and they satisfy, as usual, the commutation relation, where h bar is the Planck constant. Now, when you relate the two sides, right, you have to use an appropriate dictionary, and in this dictionary you relate the string coupling constant to the inverse of the Planck constant. Okay. In particular, this means, for example, that when you do string perturbation theory on that side, and this is something that we know very well how to do here, this on the quantum mechanical side is mapping to study a regime where h bar is very large. Okay, so this is the regime where non-perturbative effects are very important. So at that level here, you can actually use what we know about topological string to provide an exact computation for non-perturbative effect for this type of quantum mechanical operator. And on the other level, instead, you are interested in non-perturbative effect in topological string. So this is the regime like where GS is large in some sense. Then on the quantum mechanical side, this is mapped to the study of perturbation theory around small value of the Planck constant, and this is what we usually call WPKB method, and it's something that we know how to deal here. And also today and here, I'm not going to be very precise about the two sides, but let me just stress that there is a very precise way of formulating this duality, many checks, and also some proof that you can perform. And also for those who are a little bit familiar with the topic, let me also stress that the WKB expansion, so perturbation theory around small value of h bar, is something that was studied earlier in the literature. And in particular, people found that the WKB expansion for this type of quantum mirror curve is closely related to what is called the Nekrasov-Shatashvili limit of the refined topological string. Okay. But when you are in this context of quantum mirror curve, you need to include some extra non-perturbative effect, which instead make contact with standard topological string and Gromov-Witten invariants. Okay, now there are many consequences of this type of relation. One direct consequence is that what this means basically is that you can extract the Gromov-Witten invariant of this underlying geometry by studying the spectrum of this quantum mechanical operator in a regime where h bar is very large. Okay. So this, in other words, this essentially is a kind of very concrete realization of this idea that I was mentioning at the very beginning, where you have geometry, and here you have enumerative geometry, which emerge from something which is much more algebraic, and here precisely from the spectral properties of these operators. Okay, and yeah, there are also other interesting aspects also related to Borel summation. For example, one aspect of this relation is the fact that you can read the BPS spectrum and the corresponding central charge of the particle which arise when you consider, for example, M theory and you compactify on this Calabi manifold. You can read off this BPS spectrum by basically looking at the singularity in the Borel plane of these operators. Okay. But okay, so this is interesting, but it's not the main focus of the talk today. So what I really want to talk about is how we can use what we know about topological string and supersymmetric gauge theory to say something interesting on the spectral theory side. Okay, do you have any questions? Okay. So more concretely, what are the questions that we are interested in from the point of view of spectral theory? Okay. So as you probably know, and also as we discussed this morning, in general, we don't have like many operators in quantum mechanics that we can solve exactly and analytically, right? We have some toy model, and the standard toy model that we like very much is the harmonic oscillator, where we can do everything analytically. But in general, this is very hard, right? So if we want to make some progress in that direction, we need to develop some new non-perturbative tools. And what we noticed during the past more or less 10 years is that if we think of quantum mechanics from a geometrical point of view, and this is really very similar to what Balian, Parisian, Boros were doing back in the 80s. So if we take this geometrical point of view, then we can actually make contact with topological string and with supersymmetric gauge theory, and we can use tools and ideas that we have been developing in context to provide exact solution for new family of operators. Okay, and this is what I will be talking about in the remaining time. So first, I will look at a simpler model, which is directly connected to topological string, and then we will look at the particular example of the spectral problem which arises when we have a black hole perturbation theory. Okay. Okay, so the simplest example that I would like to start with is this one here. Okay, so X and P are, again, momentum and position, and this type of operator acts on a function on the real line. Okay, so when we act with e to the x, we just get a multiplication, and e to the p is like the derivative, so the exponential give a shift in the argument. Okay, so this type of operator is associated to a difference equation of this form here. Okay. And then you can prove that when you consider this type of difference equation and you ask for the eigenfunction to be square integrable and also to admit an analytic continuation on the strip, right? Because we want this to be well defined. Then in that case, you can prove that this type of operator has a positive and discrete spectrum. Okay. So there is a well-defined spectral problem which is associated to this difference equation. But then the interesting question is whether we can solve it, right, and analytically, because of course there are numerical methods, like you can diagonalize this operator numerically and you can get the spectrum numerically, but we want to have a more analytic approach. Okay.
Now for you, the wave function is pi. Am I correct?
This, yes. Yeah, I may have changed notation. Yeah, sometimes but. Okay, and then basically the claim is that, yeah, we can solve the spectral theory for this type of operator analytically, and the reason is that this operator has a particular geometrical meaning. Okay.
You have written E psi or
sorry, Francisco.
Maybe there is a typo.
Yes, it was about the fact that you have written the difference equation with E and below the spectrum as E to...
You are absolutely right. Here it should be, if I want to be consistent with these two, here I should have E to the E.
E to the E.
Yeah, thank you. And okay, so, but up to typo, this is the question. And what I want to, so the point is that, so the answer is yes, we can do that, and we can do that because this operator has a meaning from a geometrical point of view. And in particular, you can show that this operator is related to a certain type of geometry, which is a Calabi-Yau threefold, which is called local P2. Okay, so this is an example of toric Calabi-Yau manifold. It's non-compact, and we can visualize it in this way. We take CP2, and then we add a particular type of bundle, which is a line bundle. Okay. And this type of geometry have been studied a lot by many different people, especially and also in the context of mirror symmetry. And you can show that this type of geometry is related to something which look like this. Okay. So this is a geometry which is described by this equation here. Okay. Where x and p now are just complex variable, and kappa is the moduli. Okay. So this is something, kappa is what describes the shape of our geometry here. And then you can see that this is basically the classical version of our operator. Okay. So if instead of momentum and position operator here, you take just some commuting variable, you end up with this curve. Okay. So because of this connection, and because via mirror symmetry, this is related to local P2, we usually refer to this operator as the quantum mirror curve to local P2. And then the claim is that basically the exact spectral theory for this operator is given by, so the spectral theory for this operator can be solved exactly using topological string theory. Yes.
The curve is in C2.
Yeah. It's x and p are.
Yes, but it was a string kind of string worksheet. This is the question. Well, it is embedded in C2. You have two variables. Yeah, you have two variables, one equation. So it is a surface embedded in C2. Yeah. So okay. So you can think of it of a worksheet. This was the question.
Yeah, it's in C2. Yeah, it's a curve. So you may wonder, because it's true that right here we have a Calabi-Yau threefold, and then suddenly I end up with a curve, right? While when you have mirror symmetry, you have Calabi-Yau threefold and Calabi-Yau threefold. But this is a curve, so the story is slightly more involved. This is a curve inside the mirror Calabi-Yau, okay? But the historic Calabi-Yau are kind of special, and somehow you can, when you look at the mirror of this type of geometry, you can encode all the relevant information about the geometry simply on this curve here. Okay, but yeah, but there is behind this curve there is a three-dimensional complex Calabi-Yau manifold as well, if that was your concern. Okay, so then the claim is that we can solve the spectral theory of this operator by using topological string. Okay, and one quantity that you can look at, for example, is the spectrum, and in particular the quantization condition. Okay, so the spectrum of an operator depends on h bar, right? So if you consider, for example, h bar equal to 2 pi, you find that the exact quantization condition for the spectrum can be written in this way here. Okay, where the variable t here is related to the energy in a particular form. Essentially, this is given by an hypergeometric function. And F0 is the genus 0 free energy of topological string or local P2. Okay, so this is completely determined by genus 0 Gromov-Witten invariant. And this is something that we know how to compute. Okay, so at the end of the day, what this means is that the exact spectrum of this operator, okay, this operator here, at this particular value of h bar is computed exactly by counting maps from Riemann surface of genus 0 into a target space, which is given by this Calabi-Yau manifold here. And because of topological string, we know how to do that. And if we compute this F0, it turns out that this side here is simply written in terms of a Meyer function. Okay. So this is the example of the quantization condition. Okay, and I was taking this example because it's the simplest one, but you can use the same approach to study, for example, the eigenfunction. Okay, and you have a very explicit form for the eigenfunction as well, and also for other quantity in spectral theory, like resolvent, freedom determinant, and so on. Okay, so I guess the main point that I wanted to make here is that by using this underlying geometrical meaning, we can solve exactly the spectral theory of this operator using topological string theory. Now, the type of operator which appear when we study, for example, black hole quasi-normal modes are not directly quantum mirror curve to toric Calabi-Yau manifold, but they can be obtained starting from this quantum mirror curve by implementing a particular limit. Okay. And there are actually two interesting limits that you can obtain in this, starting from this topological string and mirror curve framework. In one limit, you scale the parameter in such a way that basically h bar goes to infinity. And in the other limit, instead, you take a slightly different scaling of the parameter, and among other things, h bar goes to 0. Okay. And in these two limits, you get two different operators, and you can also solve them using this time tools which come from four-dimensional gauge theory. Okay. In particular, if we go back to this picture, when we take this first limit where h bar goes to infinity, basically only this part of the spectrum survive. Okay. So this basically means that the type of operator which appear in this context can be solved exactly by using the self-dual phase of the omega background, okay? Or in other words, C=1 conformal blocks. And this is in some sense related, but it's not exactly the same to what we saw this morning in the talk by Bruno. Okay, but there are some differences that maybe we can discuss later. But so what I want to do today is not discussing this, but rather this other limit. Okay. So in this limit, you send the parameter h bar to 0, okay? And there is essentially only this part of the spectrum that survive, okay? And in this limit, we make contact with the four-dimensional version of the beta gauge correspondence. And the operator that appear in this context are also related to the Hamiltonian of non-relativistic integrable system. And usually we refer to this type of operator as four-dimensional quantum Seiberg-Witten curve. Okay, and I will come back on this terminology later. Do you have any question so far? Okay.
When you talk about quantum mechanical system, it is actually a non-local quantum mechanics. It's just an operator, a discrete operator.
It's a quantum mechanical operator, right?
Yes, but is this the Hamiltonian of the system or no? It is not. It cannot be interpreted as a Hamiltonian of a system.
Or which system?
Okay, so it is an operator, simply.
It's a quantum mechanical operator.
It's an operator. Well, which is the meaning of that operator? Which is the
when I think of quantum mechanical operator, for example, here we are on the real line. For me, it's an operator which acts on the space of function. Here, square integrable function. I have an operator which acts on the space of square integrable function, and this is typically what people call.
Yes, usually it is a local in space. It is not really very much local, this operator.
No, I think it's fair to call operator which acts on the space of square integrable function quantum mechanical.
No, but it's mostly a question of terminology.
Yeah.
So.
But for example, you see, the point here is precisely this, right? This operator here, okay, so it's nice and so on, but, you know, like from a physical point of view, what is the, you know, you can ask, is this related to anything like real world, right? So, and that's precisely the point that I want to make here, right? So this, yeah, but it's you can think of it as an Hamiltonian, right? But if you want to connect it to something like a real world, right? Yeah, yes, P1 times T1 is related to, yeah, actually, even this operator is related to a cluster integrable system. Okay.
Yeah, you can see as a order at the end of
Yeah, no, the one that I was talking about here, no.
Sorry, please.
If you take P1 times P1.
It's a sort of original driver.
Yeah, this
Sorry,
one
we
here.
have people online, therefore we should always talk on the microphone.
But yeah, so this type of operator is related to a certain type of cluster integrable system. If instead of local P2 you take local P1 times P1, this is actually the Hamiltonian or relativistic product. Okay.
I had a comment along those lines. I guess that I mean, usually you think about an operator as some quantum mechanical counterpart of a classical generic functional phase space. And that, I mean, the classically OXP is a generic function on classical phase space.
Yeah,
So, I mean, it's as good as Hamiltonian as anything. I guess that the problem, and this is the part where the confusion arises, is it's not unique to ascribe a quantum mechanical operator to this classical function.
Yes, that's true. When you go from here and you want to quantize, for example, there is a choice of ordering which is involved.
Exactly. Right? And I guess this is the source of confusion. You know what the quantum mechanical operator is by first principles.
Yeah.
And this is not the usual quantization program that the people...
That's true. There is a choice involved when you go from here to here. And like there are many ways in which you can argue why we pick that choice and not another one. And one of the way to argue about this is that this type of, when you think from the point of view of relativistic integrable system, this particular choice that you pick has a meaning. But yeah, thank you.
Sorry, at some point you said that when you send the H bar to 0, you recover classical integrable system, no?
No, non-relativistic integrable system.
Non-relativistic integrable, yes.
Like TODA.
Okay, so these are a known class of integrable system,
yes,
not
yes,
new ones.
Yes.
Okay, thank you.
Okay, but yeah, so now, okay. Okay, good. Until when I have like 35, right? At least. Okay.
I was saying, maybe this has clarifying in which. So do you have any simple way moving H bar to go from the quantum curve to the classical curve? So just if you go some slides back, no? Probably this helps clarifying, because you are making two limits on H bar, no? H bar going to 0, H bar going to infinity.
Yes.
Well, no. You just were on the right. I think, yeah, that's this arrow means.
This? No. So the point is the following. Here, of course, when you go from here to here, you just set H bar equals 0. Okay.
Somehow you said.
Here is not putting H bar equals 0 to infinity. It's a type of scaling limit.
It's a scaling limit. This is what I think the confusion is so from there.
Okay.
You see what I mean?
So, okay, thanks. Yeah, I didn't get that was your question. But yeah, so here, when we write this H bar, which goes to 0, what we have in mind is a scaling limit. And you actually put H bar equal R times H bar, let's say for D, and you send R to 0. But you also scale the other parameters in the game. Like, for example, in this operator, it's not really the best example, but you would also scale this in a certain way. While when you go from here to here, just set H bar equals 0 and nothing else. So the main point of this is that so when we have this type of operator, which have this meaning in terms of quantum mirror curve, we can provide exact analytic solution for the corresponding spectral theory, and this is nice in its own, in some sense, because we don't have many operators in quantum mechanics that we can solve exactly. Okay. However, one may also wonder a little bit more about physics, in the sense that there are many problems in physics that we can rephrase of computing. Can we compute the solution to a certain Schrödinger equation? And then a natural question that may come at this point is whether we can use this geometrical approach to say something about some problems which are more directly connected to real world physics. Okay, and as we saw this morning, one interesting class of problems are those who arise when we study black hole perturbation theory. Okay, so for example, this is a signal that we have when we have the merging of two black holes. And if you look at this very last phase, this is what is called the ring down phase of the black hole. And this is characterized by some very damped oscillation, which are due to what are called black hole quasi-normal modes, and that we are going to denote in this way. Okay. So from the point of view of quantum mechanics, these are resonances, right? So there is a particular operator which is associated to them. There is a spectral problem which has a discrete family of eigenvalue, and these have a non-zero imaginary part. Okay. And well, physically, these quantities are interesting because, for example, according to the no-hair theorem of general relativity, if you are able to measure them, then you can use that to determine, for example, the mass and the angular momentum of the final black holes. And if your measurement is precise enough so that you can measure many of these frequencies, you can even use that to test this no-hair hypothesis. Okay, so this is to motivate a little bit the study of this quantity. Let me now maybe define this the spectral problem associated to this quasi-normal mode a little bit more precisely in one particular example, which is the simplest example, and this is the one of the Schwarzschild black hole. Okay, so the Schwarzschild metric is a particular solution to the Einstein equation, right, which can be written in this way, where m is in this convention is the mass of the black hole. Okay, so this is a particular solution, but then you can ask, okay, so what happens if you know, I take my solution and I add a small perturbation? Okay. And it was shown by Regge and Wheeler that linear perturbation of the Schwarzschild metric are encoded in a relatively simple and elegant second-order differential equation, which is the Regge-Wheeler equation. Now, to write down this equation, what people do typically is that they schematically decompose the perturbation in this way. Okay, so you have an angular part, which is encoded in the spherical harmonics. You have some time dependence with the frequency omega here, and then you have a radial part. Okay. So you take these ansatz, you plug back into the equation, into the Einstein equation, and then what you get is basically an equation which controls the radial part here. So this is the Regge-Wheeler equation. Okay. So we have a second-order equation. M here is the black hole mass. The potential takes this form, well, where L is because of this particular decomposition in terms of spherical harmonics. You have the frequency square here because on the process there were some time derivative. And then you have the eigenfunction which encode the radial part of the perturbation. Okay. So this is the Regge-Wheeler equation, but as usually in quantum mechanics, when you have an equation, you also, if you want to associate a spectral problem, you have to specify the boundary condition, right? And in this case, if you want to get a little bit of intuition on what type of boundary condition to impose, typically one writes the equation in terms of the tortoise coordinate, which is defined in this way. Ah, yeah, yes, yeah, probably there is a, yeah, it could be that, yeah, yes, there is a typo, yeah, yeah, another typo, thank you. Okay, so what we are doing there is essentially we are sending the horizon at -infinity, okay. And if we write the potential, then we have something like this. And when we have this type of potential, typically the type of boundary condition that we impose in quantum mechanics are either outgoing or incoming. And if we look at the physics of the problem, at infinity, we don't want anything to come inside our universe, so we ask for outgoing. And at the horizon, instead, we ask for ingoing. And then you can show that if you impose this type of boundary condition on the Reggie-Wheeler equation, then you have a solution only if the frequency omega here take a discrete set of value, which are these black hole quasi-normal modes. And as we saw this morning in details, you can compute this quantity numerically in various ways. Okay. But then the question that you can ask is whether there exists a more analytic approach to the study of this quantity. And in particular, in view of what we saw in the previous part of the talk, whether we can think of the Reggie-Wheeler equation as the quantum curve for a suitable geometry. And well, the answer is yes. You can actually show with a little bit of algebra that the Reggie-Wheeler equation can be mapped to a quantum, what is called a quantum Seiberg-Witten curve for a particular type of gauge theory, which is the four-dimensional SU2 n equal 2 theory with 3 flavor. Okay, so let me maybe elaborate a little bit more on this side here. Okay, so what is a quantum Seiberg-Witten curve? Okay, so one way to think about it is a differential operator, which arises when we take the mirror curve to a toric Calabi-Yau manifold and we implement a particular limit. Okay, so this is related to what we saw in the previous part of the talk. And the important point is that if we consider the classical limit of this quantum Seiberg-Witten curve, then this reproduces what is called the Seiberg-Witten curve to a certain class of supersymmetric gauge theory. Okay, so we can rephrase the question, what is a quantum Seiberg-Witten curve, to the question, what is a Seiberg-Witten curve? Okay, and well, what is a Seiberg-Witten curve? This goes back to the work of Seiberg and Witten in the 90s. Okay, so one of the very powerful things that they found is that there is a certain class of supersymmetric gauge theory, which are these n equal 2 gauge theory in 4 dimensions. And for this particular class of supersymmetric gauge theory, you can encode completely the physics of those theory using geometry. Okay, and because Seiberg and Witten are the one who discovered this fact, the geometry which encodes the physics of this theory is called the Seiberg-Witten curve. And then there is, as usual, a certain dictionary. For example, if you are interested in the rank of the gauge group, then this is related to the genus of the curve. If you are interested in the central charge of the BPS particle in the theory, then this is related to the classical period, and so on. Okay. Now, so an example of a quantum Seiberg-Witten curve, for example, is this one here. Okay. So you see, we have a differential operator, and there are several parameters which appear in this operator. Okay. And from the point of view of gauge theory, these parameters have a particular meaning. Okay. So lambda is essentially related to the exponential of the gauge coupling. E is what is usually called the column branch parameter. It parameterizes, in some sense, the moduli space of vacua. And then you have this M here. These are the masses of the hypermultiplets in the theory. So because here we have an F equal 3, this means that in our theory, we have a vector multiplet plus 3 hypermultiplets. And these are the masses of the hypermultiplets. And okay, so that's fine. We can rewrite the Reggie-Wheeler equation as the quantum Seiberg-Witten curve of a certain gauge theory, but then what do we gain, right? And the useful aspect is that once you have an operator which has this quantum mirror curve or quantum Seiberg-Witten curve, then you can again play the same game that we play in the first part, and basically you can use tools which come from supersymmetric gauge theory to provide exact solution for the corresponding spectral problem. And here the main tool are what are called the Nekrasov-Shatashvili function. Okay, so these are in some sense a new class of special function which arise when we compute the path integral of these Seiberg-Witten theories. Okay, so the path integral of this theory is simply enough so that you can apply what are called localization techniques and evaluate this integral explicitly. And the result of this integral is expressed in terms of this new class of function, which are the Nekrasov-Shatashvili function. And of course, these can also be expressed in terms of known function, like you have some log of gamma function and so on. But yeah, in general, the result is usually encoded in this set of functions. And in this talk, we will denote them in this way here. Okay, so they depend of bunch of gauge theory parameters, right? This, the first here. And this is what we saw earlier. And you also have an additional parameter, which is typically referred to as the omega background parameter, okay? And from the point of view of quantization, this enter because when we compute the path integral, we have to insert a certain regulators, okay? And the epsilon here play the role of regulators. And when we map it to spectral theory, it's identified with H bar. This is because, you know, it's not exactly the Nekrasov-Shataishvili function, it's the derivative with respect to A.
Okay, you already right there.
Yeah, so because since I don't need the Nekrasov-Shataishvili function, but just its derivative, I don't.
So the dual T.
Yeah. It's just a notation for the expert.
So
because
there is a FedEx T.
Yes, yes. But I didn't want to introduce A as well. That's why I'm not using the standard notation. Yeah. But yeah, thank you. And okay, and then basically the claim is that this new class of special functions which arise in the context of supersymmetric gauge theory are precisely the one which solve the spectral problem of black hole quasi-normal modes, and also much more in the sense that you can use them not only to compute the quasi-normal modes and the eigenfunction associated to it, but also other quantities like log numbers or the gray body factor and so on. So if we go back to the example of Schwarzschild black hole, then if you take this approach, you can immediately write down the quantization condition for these quasi-normal mode frequencies, which look like this. And when you do that, then you have, of course, to use a particular dictionary between the gauge theory parameters and the black hole, which is given by this. And then you can check that these indeed produce the correct numerical frequencies which were obtained by various people in the past. Now, this is the example of the Schwarzschild black hole, but you can generalize this approach also to other type of geometry, for example, to the Kerr solution. And also, like Kerr and Schwarzschild are example of black hole which are asymptotically flat. And in this case, when you have asymptotically flat, the relevant supersymmetric gauge theory is the SU2 theory with 3 flavors. Okay. What changes is the dictionary. But then you can also look at other type of asymptotics, for example, black hole which are asymptotically ADS or de Sitter, and in this case, the relevant gauge theory is the SU2 theory with 4 flavors. Here I'm in 4 dimensions, not in 4.
And equal 4 is conformal,
yes, because
you are in ADS.
It's interesting that the conformal show up when you have ADS, but it's not. It's.
You don't know why.
Yeah, I don't have a. Maybe we can come back on this later. But yeah, it's an interesting fact. Yeah, that's also true. To have conformal, you need massless, but still, it's but yeah, okay. So this is just a restricted class of example, and you know there are much larger class of gravity background which was worked out by other people in this audience. And as I said, it's not just about quasi-normal modes; it's more general and involve also other quantity. Like there is a very nice and very explicit expression that you can get using the Nekrasov-Shataishvili free energy for the finite frequency of the gray body factor, and this is like really very elegant and nice. And a third interesting application instead is related to the fact that basically when you think of this black hole from the point of view of supersymmetric gauge theory, there are some hidden symmetry which show up. And those are related to the fact that you can have a permutation of the masses inside the within. And this is apparently useful when you are interested in study stability, for example, in the case of Kerr black holes. Okay, so I'm almost at the end. So let me briefly conclude. So what we saw during the more or less last, I don't know, 20, 30 years is that string theory and supersymmetric H theory have provided us with many interesting new ideas and also several powerful tools which have given interesting application in various fields. And here today I focus on application to spectral theory, and we saw that we also have some interesting connection with black holes, and this is something that we just started to explore. And yeah, so thank you very much for your attention.
Okay, questions, comments?
I understand the mathematics, but the question is, have you any idea of the meaning, of the physical meaning, or of this quantum cyber-Witten curve? How you connect it to the physics of a black hole?
Yeah, so what I show today is rather how those two are connected. Why they are connected, this is maybe something which requires extra thought.
So as a person coming from classical gravity, I have a curiosity. Some of the applications that you mentioned, quasi-normal modes of Schwarzschild, stability of Kerr, those are results that can be derived, say, with classical methods. So what do you really learn?
Well, for example, if you want to prove stability, here we are talking about mode stability, and I'm talking about mathematical proof of mode stability. For example, mathematical proof of mode stability for the extremal case of Kerr black hole, this is something that was like found by this lady just very, very recently. So,
and in terms of computing modes or tidal of numbers,
okay, so
there is some.
I mean, I understand. So your point is basically, we know how to do numerics for these things. So what do we learn? Well, let me just mention some examples. Numerics work well when n, which is this quantum number, is low. Suppose that you want to go to large n. Numerics is not that good. If you want to go to the extremal limit, you can do numerics, but it's not that good. And here the extremal limit has a very nice interpretation in terms of the coupling limit of cyber-Witten theory, and you can get something which is very simple. You can actually get even more precision than what you get numerics. But so you can do, if you want, you can go in the regime where numerics maybe is a bit harder. But I think the main motivation behind this type of approach is not to beat the numerics. Okay? So if you are interested in the, for example, I don't know, analyzing the gravitational wave signal, right? The first, what you can usually extract are the first one or two modes, right? And for these modes, numerics give you all the digits that you want. So I think that there are places where you can maybe do a little bit better in some sense than numerics, but this is not the main motivation behind it. The main motivation is really to have some new analytic approach. And when you do that, you see that there are some things that show up, like some hidden symmetry and these kind of things.
Thank you.
Let me add a comment to this question. Gauge theory also suggests what are the right variables to use. Not the right, let's say, gauge theory organizes the computation in a different way than what you would do it for numeric. And sometimes it can suggest what is a definition for a quantity that is easy to compute. For example, for love numbers, it's very hard, it's not known what is the right definition of love number for not the static case, the non-static case. Gauge theory can suggest what is easy to compute from the gauge theory side. Now we are studying this type of questions, and gauge theory gives a very nice definition of what could be the love number for the non-static case. Let's say it's a different organization of the computation, in which you can compute some quantities analytically, Of course, we cannot give the full answer, but in some regimes and so on. Therefore, it can suggest which is the regime which is easy to look at. What are the parameters that you should? I mean, we are learning. We don't know. As Alba says, it's not a competition with numerics. And numerics, you can do a lot of things, but maybe having some insight of what to look at could be useful.
I have a question. So in other theories, in modified gravity theories, actually I will talk of this tomorrow, there are some black hole solution with scalar fields, so the Noether theorems are not satisfied. In that case, people in the classical gravity community is trying to compute the quasi-normal modes. But I'm wondering whether this approach may be used to compute quasi-normal modes in black holes in modified gravity. My doubt is that in that case, one does not have an analytical solution of the solution. So the solution is non-numerically, let us say. So one knows the Lagrangian, the equation, but the solution is non-numerically. Do you think that this approach may be applied also in situations in which you know the classical solution only numerically, or you think it's too hard?
So okay. First, I don't know. I have to see the potential, right? Depending on what potential you have, you can see if your potential can be mapped to a Seider-Witten geometry, right? Then if you can do that, then yes. Otherwise, no. And also the important point is that there are Seider-Witten theories which is easier to do the computation, and other for which is hard. So depending on whether you can map your potential to a quantum Seider-Witten curve, and depending on which Seider-Witten curve you have, the solution may be simpler or harder.
I see.
But I don't know the potential just because I don't know, so I cannot say.
Hi, just a couple of curiosities. So in the first part of your talk, when you introduced the framework, you said that enumerative geometry is an emergent phenomenon. So what do you mean exactly as emergent phenomenon?
I mean that, so enumerative in this Gromov-Witten invariant, right, are something which are very geometrical, right? It's counting of holomorphic maps. And the point here is that there is a class of operator, quantum mechanical operator, right? So in principle, quantum mechanical operator, it's really about algebra, right? It's not much about geometry. But if you study the spectral traces of this operator in a certain limit, you can extract this Gromov-Witten invariant. So emergent in the sense that you can extract them by using operator theory. So you have enumerative geometry which emerge from operator theory.
Okay, so it is emergent in the sense that you have to take some particular limit to see it come out.
Emergent in the sense that these operators are not something which are, let me maybe go back a little bit. You have emergent in the sense that you can compute them by using a completely different framework, which is not really a geometrical framework from that sense. In the same way in which, in the work of, for example, this, I'm not sure, maybe that's not a very appropriate example for some of the audience, but like this example that I was saying about Witten and Kontsevich, right, where you have intersection theory on the moduli space of Riemann surface, you can extract this intersection number looking at matrix model, which is something which is more algebraic. So they emerge from something which is very different and much less geometrical.
And just another curiosity, at some point you mentioned new that your results are pointing towards new integrable theories, or am I wrong?
No, I didn't mention that. What I mentioned is that you have new exact solution you have a class of operator for which you can get exact analytic solution.
Okay. New exact solution of already known integrable theories.
Well, okay. For example, let me take this operator here. Okay. So this operator, right? People know that this is related, for example, to cluster integrable system and so on. Okay, so it's not a new operator in some sense. But what is new is the fact that we can solve analytically its spectral theory.
Okay, okay.
So the fact that this operator is not a new operator in some sense, it's just a solution that is new.
Okay, thank you very much.
Thank you.
I have a couple of comments. One is related to the physical interpretation of this connection between, we don't have a receipt, but we have a proposal which we would like to test, and it's related to the duality between M5 branes and M2 branes wrapped around this sub-Newton curve. It's only just to mention that might be, and once again, string theory can help unveiling this hidden connection. And the other one is about black holes in higher derivative theories. Clearly, if you build black holes using branes in string theory is a higher derivative theory of gravity. Clearly, the higher derivative expansion is completely fixed by the consistency of the theory with higher spins. And we have studied quasi-normal modes of black holes in theory or intersecting D branes, even D3 branes or whatever. So I don't see any. In fact, actually, also we studied objects which are non-singular, like microstate geometries, circular fuzzballs, and everything is related to the photon sphere.
Yeah, you are absolutely right. Thank you.
Hi. Thank you for the talk. So I was thinking, so if you consider general enough solutions of four-dimensional
I think your phone is, your microphone is not.
Run out of battery, right? Okay, let me try again. So then these more general solutions of 4DGR have this NAT charge, right? Which is a very exotic charge because, well, the interpretation is not so clear, like from a classical point of view. I was wondering whether by this correspondence with quantum cyber-Witten curves, you could shed some light on the interpretation of this charge, right? Like, would it be mapped to the masses of the...
The short answer is that I don't know.
Okay.
But it's,
okay,
yeah,
okay.
Maybe we can talk more
sure.
Later.
We can maybe start directly the discussion session. We have 15 minutes before the coffee break. We can call Bruno in such a way that you can ask all the questions to Bruno and Alba. If you can come.
Can I?
First, we thank Alba.
Can I interrupt?
Just leave it because somebody can ask you something about the.
All right. I just had some. Actually, consider the NAT charge, and the equations are similar. It may not be clear, but the approaches are similar between the ones I talked about this morning and Alba's. But the short answer is no. We don't have any new insight towards NAT charges. Although I can say that the problem is solvable in the same way that this problem is solvable.
Apollo, have any questions?
I have a question for Alba. So related with this, the need of a potential, right? So you were focusing on the Regge-Wheeler potential. I was wondering, is there a duality for the Zerilli potential? And can you like explain the isospectrality?
That's a good point. Short answer, I don't know, but I think that should be reflected on the gauge theory. It's just that I didn't really look at that.
I have an answer for this. There is a dual of, in terms of Cyberon width, it's a quiver. It's not just SU2 gauge theory. It's a quiver with two gauge theory. In general, if you have any ordinary differential equation with Fuchsian singularity, you can always map to a Cyberon width curve. And just the number of Fuchsian singularity refer to the number of gauge group you have. Therefore, this is a very good point.
If I may say something there. So the Regge-Wheeler and the Zerilli equations of perturbations, they are a special limit of the Tchaikovsky perturbations when the rotation is set to 0. Now, if you solve the Tchaikovsky equation in the limit where A is equal to 0, you see that there is only one family of modes. One family. So there is only one frequency. So that's why they have to be isospectral. Because coming from the Tchaikovsky perspective, there is no split between Regge-Wheeler and Zerilli modes. There is only, you solve the equation for 0 spin, the Tchaikovsky equation for 0 spin, and you get what you get. So isospectrality is something that that emerges just because you are following this historical approach of Regge-Wheeler and Zerilli. But from the perspective of the Tchaikovsky master equation,
I agree with you.
This is I
was just wondering whether there was a different theoretical understanding of this without involving the spin, focusing on variance.
The quiver language, these masses, they are special. They are not generic masses. They have to be special to the black hole parameters. The masses of the quiver in the gauge theory language, they have to be special. They are not generic masses. So that's part of what Oscar was saying. It's a very specific quiver that gives you this.
So I'm getting a little confused by the discussion, so I wanted to ask a basic zoom out question. So the impression that I got from this idea is that basically you have, from black hole quasi-normal modes, let's say you have some equation, right, that you want to solve, and then you realize that this is the same equation that the Seiberg-Witten curves give you, and so that's the connection, right? The connection is through the differential equation, and then then we want to maybe interpret this as there's some hidden conformal gauge theory attached to the black hole, but this is speculation, right? But then there was a comment that maybe there really is a relation, and so what I guess my question is really, how should I? At the moment, I see the connection through the equation, right? There is some family of differential equations, and this family of differential equations can be generated by looking at supersymmetric curves, right? Fine, but then how does this work then, for example, for the tidal love numbers, right? Because this is some other equation that you're solving, and how would you, like, if you do say that the gauge theory is equivalent in some way or captures the black hole physics, then how should I see this, right? Like, where does the gauge theory live? Is this a meaningful question, etc.?
But for example, the love number, I think you can define them starting from the Tchaikovsky equation, right? By imposing some other type of boundary condition.
Okay, so it's the same kind of.
Yes,
okay.
And since the Tchaikovsky equation, you can solve it using that, then you can also.
Okay, so there's no. Okay, so you're still just going through the same equation.
It's a bit more than just having the same equation, because I was showing in the morning that there is, you can think about the family of solutions with these monodromy parameters. So here you basically have the same words, and they are translatable. I mean, they have, in this case, it's the derivative of the free energy. They are variables in which the problem you actually want to solve, they become trivial. So a bit like actual angle variables for this problem. So it's a bit more than having the same equation. You have some sort of same symplectic structure that allows you to write the solutions in an easy way.
So, okay, so if I can rephrase that, tell me if I'm right or not, but it is the same equation, but we know a lot about supersymmetric gauge theories, which allows us to then say, oh, but we have all these tools, and so we can attack this equation in a much more efficient and in a much more elegant way, and to find these solutions in an analytic way, or you know.
Well, I guess elegant is sort of depends on taste, right? But it's for sure. It's the if you have a same classical system, suppose that you begin with, you may have some completely different quantum system out of that. Okay, you may have different quantum systems which come to the same classical limit. What I guess the philosophy behind this is that you can think of the equation, the differential equation, some sort of classical system. I know it's quantum, but anyway, it's some differential equation. But the quantum version of that, from either the conformal field theory or the gauge theory, makes sense. And it's actually the quantum version of that in the CFT or in the gauge theory. So it's a bit more than just having the same equation.
And so can I ask questions about, like, okay, if I want to have a physical interpretation, right, of this gauge theory related to the black hole, can I go further and say, okay, I'm going to study some other question in the gauge theory, and this will tell me something else about the black hole?
For example, about
does this make sense?
Non-linear, like when you do perturbation theory, we know that this connection holds at the linear level, but what about going at the non-linear?
For example,
I think it's a good question, and I don't know if this connection still holds beyond linear. But if there is a deeper meaning, probably it still holds beyond the linear perturbation theory. I think this is an interesting question. I don't know. Maybe other people know. But.
Hi. I'm not sure I have a very clear question, but I'm trying to understand the game because I find it very interesting. So if the game is that the Regge-Wheeler-Zerilli equation has some association with the Seiberg-Witten equations, then in the game of Seiberg-Witten, there was a lot of work done to associate it with the Picard-Fuchs equation, which are linear systems, invariants related to W algebras that are and allow you to classify very clearly all the solutions. So I'm wondering whether this machinery can help also in classifying the solution on the black hole side and or something like that. I don't know how far you have gone with this.
Maybe I can start and then you. Yeah. So I'm not sure about classifying. About Picard-Fuchs, usually like Picard-Fuchs equation is about the prepotential, right? The F. Because you see, we have something which now I cannot really go, but so I think Picard-Fuchs was. I mean, it's very nice, but Nekrasov, this Nekrasov-Shatashvili function is more than this in some sense, right? Usually, when people think about Picard-Fuchs, they think about the classical periods, right? Nekrasov-Shatashvili encodes this and more. So in that sense. Here we are using a technology which is, then again, it's depending on what you want to look, but for this point of view, it seems to me that the technology of Nekrasov and Shatashvili is more advanced than the Picard-Fuchs.
But do you need it? Do you need all that? Isn't that enough? I mean, the similarity looks like.
You mean if I need the Nekrasov-Shatashvili,
yeah,
I can just
can't you go far enough also
we really need Nekrasov-Shatashvili because I think Picard-Fuchs only give us the, like when we think in terms of WKB, right? Like we have an H-bar expansion, Picard-Fuchs, they give, okay, then, so it doesn't, so Picard-Fuchs is really related to, in some sense, from what, the way I see it is, that it's more like the generating functional of like WKB expansion. Nekrasov-Shatashvili resound this WKB expansion. So from that point of view, it's more, okay. I see. Maybe someone else.
I have a little comment on this issue of Picard-Fuchs equation. Yes, in the paper of 2019 by me, Gregori, and my supervisor Fioravante, so we found, we showed very briefly, without explaining much actually, that there are also higher order in WKB Picard-Fuchs equation. Yeah. Yes, and we have a conjecture, but it's not published, that they resum to some exact Picard-Fuchs equation. Yeah, yes, but it's just a conjecture for now.
Yeah, but you are absolutely right. There is actually various ways of resumming this WKB period. Here I was mentioning Nekrasov-Shatashvili because but there are actually other techniques, and you and Davide are familiar, for example, with the like TBA type of techniques, and you actually also show that this is also very strong in this type of example. Yeah. So.
Comment on the thing. It's working. Okay. No, the point is that the Picard-Fuchs equation is satisfied by classical periods, okay, the supergravity ones, and they correspond to the very deep infrared of the gauge theory, while turning on these epsilon parameters, the omega background, probes the gauge theory in the ultraviolet, okay? And so sees the microscopic structure in the path integral. And that's the novelty from the viewpoint of the gauge theory, which was not catched at the time on the side. And on the other side, this gives the technology to give these exact solutions of the differential equations, which were not known earlier.
Anyway, I think that what Anna is saying, I agree with what you're saying. I mean, what they're saying is that the Cyber and Witten is just the limit. This gives the information of the semi-classical expansion in gravity, and this is true. But still, what Anna is saying is that in a lot of years we develop and we learn a lot about about the limit, and all this we can use now to see what we can say about black holes in the semi-classical limits, of course. Nekrasov-Shatashvili say something more. They say you don't need even semi-classical limit. You don't need large charge, large momentum, large energy, and so on. But still, to see, I think it's interesting anyway to look at the limit in which, because in that limit we have very strong results, and maybe we can learn something.
Hello, thank you very much. So maybe to continue a little bit from what Daniel was saying, with all these connections that we've all been discussing, does it mean that there are some hidden symmetries in the Tchaikovsky equation that people coming from classical GR background were not aware of, that you and your collaborators and other people working on these connections have discovered? And if yes, do they have any physical interpretation, or can you say something about them?
So this was not this was Rita Teixeira da Costa and her collaborator. You are referring to this, right?
I'm not familiar with that paper, but possible, yes.
Okay, so can you rephrase the question?
Are there any hidden symmetries that people in classical GR were not aware of before that now they've been discovered? And is there any physical interpretation of this?
So this is an example where you have some hidden symmetry due to the fact that the mass permute in Cyber-Witten. Okay. And I'm not sure what is the physical meaning, but it's useful because it allowed you to simplify some.
The question is whether you take the original equation, have you identified additional symmetries in that equation that are useful?
Yeah, so the thing is that if you take the, for example, in this case, the Chukovsky equation, if you just write it in terms of black hole parameters, there are some symmetry that you don't see. When you rewrite it in terms of quantum
Okay, so the answer is yes. Now, what are these symmetries?
Yeah, so the thing is that when you rewrite this in terms of the quantum Cyber-Witten curve, from the point of view of the gauge theory, okay, these symmetry are permutation of the masses.
Yes.
On the black hole, this is some exchange of the parameters.
Which parameters?
I don't have the dictionary here. No, but this is about Kerr. I was showing about Schwarzschild.
Okay, no.
Yeah, yes, but
Okay,
it's this hidden symmetry that okay, yes. So basically, so in this case, you see, it's not really, because, you know, if you permute the mass, it's not, but when you go to Kerr, it's more interesting.
Okay, so what are the symmetries?
Yeah, these are the theta parameters that I had in the morning.
Yes, but in terms of the parameters of the equations, what are the symmetries?
These are, in my language, so you always have some S here, and this is omega minus n1.
Bruno, I think, yes, you want in the gravities, yes.
No, this thetas, it's related to the mass that she defined.
Okay.
So you have this for the outer inner horizon, and for infinity. Infinity is a different point, by the way, but here you have 2s.
What is S?
S is the spin of the, this is still possible. So this is, I think it's 4im. But you don't see, right? I mean.
So what is the symmetry?
Well, the symmetry would be to change those, but to interchange those,
which?
Theta plus and theta minus.
Okay, thank you.
What is plus and minus? You don't see.
Yeah, this is T plus and minus. Sorry.
Thank you.
No, but I mean, there's an extra thing that you also have some kind of resurgence happening.
And the T's, can you remind me what the T's
T
are?
is the temperature of the black hole. It's
Okay.
R plus minus R minus over 4m.
Okay, and T plus minus refer to R plus and R
the temperature
minus?
of the outer horizon and inner horizon.
R plus and R minus.
Yes.
Okay.
Essentially, you're like changing the two horizons and the two velocities of the.
But if you want to understand this, you think in terms of physical parameter, means that you have to take omega or something complex, which doesn't make physical
No, in this
sense.
case, it's what he said that, right? You exchange the inner and outer horizon and you change the direction of rotation of the black hole.
You don't exchange the inner and the outer horizon, only these parameters.
But here, this is what you do, right?
Well, that's an extra parameter in the equation which is related to the lambda there. Well, and in the morning I call that T naught. You don't change that. You may change the mass parameter.
Okay, so one parameter is changed and the other remains the same.
So you have to think of those as free, as independent. That's why you don't see that from the Tolkovsky equation. But there is another point which is very important, that because of resurgence, the expansion around lambda 0 and lambda infinity, they are related. And this is also something that you don't see from the Tolkovsky equation. And this is very important for when you take these asymptotics of the angular eigenfunction near infinity, near omega infinity, etc., and the structure of the WKB expression itself. You also have that here, although it's not transparent. And I mean, you work with the Tolkovsky equation for 40 years and you could not see that.
Okay, thank you.
So related to this, I think this is just a realization of Tolkovsky-Starobinsky identities, right? Like, and if not, like, are the Tolkovsky-Starobinsky identities realized in the Cyber-Witten classical curves, quantum curves scheme?
Can you remind me of Tolkovsky-Starobinsky?
So in Petrov type D spaces, in perturbation theory of Petrov type D spaces, there are some identities relating the psi0 Tolkovsky variable and the psi4 Tolkovsky variable. And they are like fourth order differential identities. And actually this psi, if you move, sorry, this psi infinity, I think it's exactly a Tolkovsky-Starobinsky constant.
Well, I don't think it is, because the symmetry, at least the first symmetry that we talked about, they don't change this one.
Yeah, the Teukolsky-Starobinsky constant is invariant under the Teukolsky-Starobinsky identities.
But more importantly, this in Teukolsky equation has a different meaning than this.
Yeah,
In the language that I told you this morning, they are associated to regular singular points. This is a irregular singular point.
Okay,
the structure, the mathematical structure here is different, but it is not only interchanging parameter in the differential equation.
No, I know. What I'm saying is definitely not just interchanging parameters of the equations either. It's like, and this is in Chandrasekhar's book, for instance, like, so it's known for a long time. And actually my question before Bogdan's question was whether these particular symmetries, like the Teukolsky-Starobinsky constant identities, which are like very surprising because very involved, fourth order differential equations relating one variable to the other, had any particular realization in here, or, you know?
Yes, somehow I don't think they are related, but because there you are basically solving the same physical problem, but with a different parameterization. Instead of having psi 0, you have psi 4. It is the same thing, right? If you do some time reversal and there is a set of physical symmetries, discrete symmetries, but physical symmetries that related to. This is not related by any physical, at least to my knowledge. It's not related to any physical interpretation. Like I told you, to really see this, you need to consider these functions to be complex numbers. And so this is not related to, in my mind at least, it's not related by physical symmetries.
Yeah, no, I agree. But then his question is, what is the gauge theory realization of this symmetry? And I don't know.
That's a very good question.
You see, so to appreciate the full symmetry, you can take just, for example, ADS Kerr-Newman black hole. You have the mass of the black hole, the angular momentum, the charge, and the size of anti-de Sitter. This rotation of the four mass is a very complicated exchange of these parameters. You have the map and you see exactly what you should exchange. From the gravity side, seems there is no relation between these. I'm sure that many of this symmetry has been already known in other contexts and so on. This is just, for gauge theory, it's a trivial symmetry. At four mass, there's no difference between them. From black hole physics, is completely surprising. This is related mass, size of anti-de Sitter, charge of the therefore, it's a different, let's say, it's a different language. And I believe that this is not a competing language. What we should try to do is to see what we can learn from one side, from the other, and so on. I mean, okay, other questions?
Yeah, I guess just to want to enforce the point, there is this extra bit of information come from S-duality. And this is something new. This is purely Seiberg-Witten or string theory, right? And there is absolutely no way by looking at the equation you would be able to foresee that. This is a bit surprising. I mean, you solve that. I mean, you tell a mathematician that, or you look at the differential equation, Fuchsian differential equation. It's been known for 150 years, and you work your way around the connection problem very easily. And then suddenly, when you put an extra singular point, and in this case, an extra mass multiplet, you have to know all this machinery to solve. They'll tell you you're crazy, right? But this is what it looks like. There's no way around it. I mean, it's even if you work, I mean, without the Young Mills, even if you work in pure CFT, that you need the full Virasoro algebra to understand the classical problem. It's completely nuts. But this is how we get out. This is how I did it.
Sorry, let me check if there is any question from the people at home. Have you seen any? I don't see anything in the chat. Okay. Okay, I don't see. You can always unmute yourself and ask questions, please. Okay, any other questions or comments? Okay, if not, we stop here. There is a coffee break now, and we meet tomorrow morning at 10. Okay, tomorrow, remember, we have 2 lectures in the morning. The first is at 10, no? It's okay. Sorry, we thank again the 2 speakers.